before we get into finding the adjoint matrix, we can go ahead and take a stop and look at properties of determinants. Some of these properties are really useful in terms of identifying what kind of matrices are actually going to have inverses. Because remember, if the determinant of A is equal to 0, it doesn't have an inverse. So it kind of gives us an indicator of what kind of matrices are going to produce an inverse, which, if you remember, when we look at a matrix, specifically AX equals B, or the augmented matrix, we think about each row as an equation. So it helps us figure out what types of equations are going to give us a solution, and we'll see what that looks like in a couple weeks. So the first thing is transpose. If this is the transpose of a matrix, so T is for transpose. And remember, to transpose a matrix, we take the rows and make them columns, or take the columns and make them rows. But if AT is a transpose of a matrix, then the determinant doesn't change. So the determinants are the same. The second one is if any two rows or two columns of a matrix are the same, then the determinant equals 0. And it turns out that this is also true if our rows are linear combinations of each other or columns are linear combinations of each other, then our determinant is equal to 0. Which means that that kind of matrix isn't going to have an inverse, which means we'll see later, a solution or a system of equations for that matrix isn't necessarily going to have a solution. Then we have 0 rows. So if all the entries in a row or column are equal to 0, then a determinant equals 0. So that's pretty clear to see. If we end up with zeros at the bottom, the determinant is equal to 0. And you can see that easily with this diagonal method where everything's going to be multiplied by 0. And then we have this one, and this one correspond to our row operations. So how does our determinant change when we do our row operations? So if we go ahead and swap two rows, so row operation 2, so essentially if row 1 and row 3 change places, then the determinant changes sign. And the reason for that is because we have our cofactor signs. Notice each row is the opposite of the other. So if I multiply this row by -1, I'll get the row below it. So if we swap two rows, then the determinant changes sign. If we multiply a single row by a constant, so let's say I say row 1 equals row 1 times 2, then my determinant is also multiplied by that constant. So be careful with this one because this is for a single row. You're not multiplying the entire matrix by a constant, you're just multiplying a single row. So if A looks like this, and I multiply this row by 2, then my determinant would be multiplied by 2. If I also multiply this row, the second row, by 2 to get 214, then my determinant would be multiplied by 4. 2 for this one, and 2 for this one. And then we have this one here. So our elimination step, our row operation 3. If we perform an elimination step, so solely by saying row 1 equals row 1 minus a row 2, notice the elimination step, the row you're replacing is not multiplied by anything. So this is our elimination process where we replace a row by adding it or subtracting some constant of another row. Then our determinant doesn't change. And we'll step through an example showing how our determinant changes with each of those row operations. The last ones, so here we have matrix product. If A and B are both matrices, then the determinant of A times B is the determinant of A times the determinant of B, so the determinant is multiplied separately. For a triangle matrices are really nice. These are the ones where we have essentially a lower triangle of zeros, or an upper triangle of zeros. But these ones are really nice because the determinant is just the elements of your diagonal multiplied by each other. So here it would be 1 times 4 times 6. Here it would be 1 times 2 times 3. So these ones are really nice to work with. So if we can go ahead and somehow get to a triangle matrix, the determinant's really easy to calculate. And that makes sense if you look at the determinant here, or if you look at the diagonal method as well. all of these entries are 0, or all of these entries are 0, meaning you're multiplying things by a bunch of zeros. And then lastly, the inverse matrix. When the matrix, if B is equal to A inverse, then my determinant is 1 over A. So if determinant of A here is equal to 4, the determinant of A inverse is going to be 1/4. And those are determinant properties. So these are, once again, these are really nice to help determine how our determinant changes over time as we're doing row operations, or helps us indicate what kind of matrices are going to have inverses, which means what kind of matrices correspond to systems of equations that are going to have solutions. So that's how we can use these properties of determinants.